we have a significant focus on improving battery performance, safety, as well as providing the possibility to lightweight the battery pack. Our solutions include those that are located within the cell and components such as cathode binders, separators, and solutions that are located outside of the cell, including bus bars, high voltage connectors, as well as coolant lines and venting. I'd like to introduce myself as well as two of my colleagues who are going to discuss this topic in much greater detail. My name is Brian Baleno. I'm the head of automotive marketing, and I'm joined by Stefano Montani, marketing manager, as well as Rui Liu, who's a marketing manager for battery systems. We're going to start with the electrical components, and we're going to start by discussing some of the biggest challenges that engineers are facing, including thermal runaway and thermal propagation.
I am Stefano Montani, marketing manager for transportation cluster. Electric components, such as bus bars and terminals, which allow the electrical connection between cells, are nowadays extremely challenged by a new regulation which originated from China and that later spread to the US and the European Union. The market is increasingly asking for electrical components to maintain their insulation performances during and after high heat exposure. The requirements are very diverse, and they range from an exposure to 400 to 1000 degrees Celsius for a time that goes from 5 to 20 minutes. The aim, in this case, is to stop or slow down a fire to propagate to the overall system, and therefore to give time to the passenger to escape the vehicle in case of a fire event.
Thermal runaway and thermal propagation seems like a huge challenge for any thermoplastic material. What kind of material could really withstand such harsh conditions, and what kind of processes could be used to insulate bus bars?
The first thing to keep in mind is that flame retardancy does not directly translate into resistance to a thermal runaway event. For this reason, we have broadly tested materials within our product portfolio in order to identify options able to withstand exposure to convection heating and also direct flame torch testing. We have identified some interesting candidates within our A-Model PPA and Rhiton PPS product family, as well as within our Kitaspire Peak and Avaspire Pike product lines. Our material can resist for 5 minutes convection heat exposure, as well as 6 minutes direct flame torch testing at 1000 degrees Celsius. The insulation can be applied to the copper bus bar by several different methods, including overmolding, powder coating, and also extrusion.
So let's shift our focus to battery modules. Do materials exist that can address those challenges, and do the same challenges exist for battery modules?
Battery modules are collections of cells. In order to insulate each cells one from the other, and also the full battery stack from the metallic battery enclosures, we need spacers or insulation plate. Those insulators need to withstand the same flame-resistant requirement as the other component discussed so far. For this reason, we developed a new-sided LCP, liquid crystalline polymer, which allows to resist 30 minutes exposure at 400 degrees Celsius while offering unmatched flowability and allowing to fill parts with a thickness of 0.5 millimeter.
Now that we've covered battery modules, let's shift our focus to battery cooling. Battery cooling is another significant challenge that battery design engineers face. Here we developed a brand new Rhiton PPS grade that's designed for battery coolant lines. Additionally, we've developed some new Kitaspire grades that were tailor-made for coatings to coat the battery insulation plates. We're going to discuss those in much greater detail.
Rhiton PPS is a well-recognized and known material in the market for thermal management system, mostly due to its intrinsic flame retardancy as well as dimensional stability and chemical resistance to refrigerants and coolants. However, extrudable PPS currently on the market are not offering the V0 flame retardancy that is normally desired in order to resist to thermal runaway event. For this purpose, we have developed and launched a new version of extrudable Rhiton PPS, which allows to achieve a V0 rating up to 1.6 millimeter of thickness and therefore constitutes a perfect candidate for battery cooling lines. On the other hand, Kitaspire Peak can be applied as a coating to battery cooling plates in order to work as electrical insulators as well as provide a strong barrier against flame propagation.
Let's move beyond battery cooling to battery venting. What are the incumbent materials that are used today, and what are the limitations of those materials? Let's explore how we can develop and offer better performing solutions for battery venting.
Battery venting systems are in principle very simple components because they are not exposed to high temperatures during operation. However, in order to ensure long-lasting sealing performances, as well as to allow evacuation of gases formed during thermal runaway event, our Rhiton PPS gives higher reliability over incumbent solutions, mostly based on polypropylene.
We are also working on lightweight solutions that offer the potential to not only lightweight the battery, but also open up the design envelope for engineers to find more space to improve power density. What do designers need to account for when they focus on replacing metal in the battery enclosure?
Anytime metal to plastic replacement is considered, it is never just about weight reduction, it is also about part integration, space saving, and increase in power density. Our long glass fiber product and continuous glass and carbon fiber composite have the potential to achieve a weight reduction by 50% as well as an increase in power density by 22%. At the same time, they are allowed to match the flame-resistant requirement according to the standard UL 2596. Finally, our solution allows achieving EMI shielding protection, thus allowing to avoid any interference between electrical components.
Thanks, Stefano, for all the great insights on how we can improve battery system performance as well as lightweight the battery. Now let's focus on how we can improve power density with our solutions inside the cell. And I'd like to introduce my colleague, Ray.
Thanks, Brian. I'm Rui Liu, Program Manager of Battery Material Platform. Beyond all these interesting applications in battery system, if we look a little deeper and closer, inside the battery cell, we do offer a wide range of products, not only for today's lithium-ion battery, but also tomorrow's next generation. For example, solid PVDF is used for binder and separator coating. It is already very well known for today's lithium-ion battery. We keep innovation on the products and also investment to match the future market demand. And again, it's a family of fluorinated additives. It is used for electrolyte for batteries to increase high voltage, fast charging, and better cycle life. Solgan is a new technology for cheaper and safer next-generation battery. For the ultimate target of all solid-state batteries, we are investing a lot of resources and efforts in the development of inorganic material for solid electrolyte and polymers for binders. At the same time, we are also working actively with our partners in battery recycling technology. With a dedicated team in battery cell chemistry, 2 applications labs in Europe and Asia, and all the scientists around the world to develop new molecules, we are committed to develop a solution for your battery today and tomorrow.
And now you know how we enable
cleaner, safer,
and a more energy-efficient mobility.